Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the lectures until now, we have studied modal analysis of undamped and damped systems. We looked at how to obtain modal characteristics of a system from its spatial model. The spatial model will consist of the mass, stiffness and damping matrices of the system. However, the experimental modal analysis is based on analysis of responses or response model of the system. This response model consists of frequency response functions in the frequency domain and impulse response functions in the time domain. So, experimental modal analysis basically analyzes these FRFs and IRFs to determine the modal characteristics of the system, that is the natural frequency, mode shapes and damping factors. So, in the later lectures we are going to study how to measure the frequency response functions and impulse response functions and how to analyze them to obtain the modal characteristics. In this and the next lecture we are going to talk about characteristics of FRFs, okay, and in this particular lecture we are going to focus our attention on characteristics of FRFs of a single degree of freedom system. So, we are going to talk about FRF characteristics, right, and focusing attention on single degree of freedom systems. A brief outline of the lecture is as follows. First, we are going to define different types of FRFs, and then we are going to look at how FRFs can be presented graphically. Then we will look at the FRF characteristics of a single degree of freedom system with viscous damping, right. And then we are going to also study the concept of stiffness line, mass lines and how to identify mass, stiffness and damping of a single degree of freedom system from the FRF. So, the first thing we are going to talk about is FRF types. As we defined earlier, the frequency response function is basically the ratio of the response of the system in the frequency domain and the force applied causing the response in the frequency domain, right. And the response now can be described either by the displacement of the response, velocity of the response or acceleration of the response. And depending upon which parameter is used to define the response, there are three types of FRFs. So, the first is what is called as receptance. This receptance FRF is denoted by often by alpha omega is ratio of the displacement response of the system in the frequency domain and the force applied on the system in the frequency domain, right. Then we have what is called as mobility. This mobility often represented by y of omega is ratio of the velocity of the response in the frequency domain, that is v omega, and a force applied in the frequency domain. And because these quantities are defined in the frequency domain, they are at a certain frequency, right. So, each frequency basically refers to a harmonic force acting on the system, and the response corresponding response is also harmonic, and therefore, the v of omega can also be written as I omega times the displacement of the response at that frequency, that is I omega into x of omega, right. And therefore, we see that I of omega into x of omega upon f of omega can also be written as I of omega into alpha of omega. So, this shows that the mobility is basically related to the receptance of the system, right. So, if you multiply the receptance by I omega, we get mobility. Another FRF which is defined that is called as inertance FRF or accelerance, and this is denoted or maybe we can denote it by A omega, and this is ratio of the acceleration of the response and the force causing that acceleration, both defined in the frequency domain. And the acceleration can be written as I omega times V omega, right, because the motion is harmonic. So we can do that, and therefore we can also write the expression as I omega times y of omega. So if we have the mobility, and if we multiply it by I of omega, we get the inertance of the system. And because y of omega is nothing but I of omega into alpha of omega, we can also write this expression as minus omega square alpha of omega. So therefore we see that the receptance, mobility and inertance, they are related right by these expressions, and if any one of them is available, the other two can be determined. Now there is also something called inverse descriptors of the FRFs, right, referred as inverse FRFs. These inverse FRFs are basically defined as ratio of the force applied on the system in the frequency domain and the response of the system in the frequency domain, right. And again, depending upon how the response is described, whether by displacement, velocity or acceleration, there would be three types of inverse FRFs, and the first one is named as dynamic stiffness. Okay, often denoted by Z of omega, and this is nothing but the ratio of the force applied in the frequency domain and the response in the frequency domain, right. So that is nothing but the dynamic stiffness. Then there is something called impedance, right. This impedance, if we denote it by I omega, is ratio of the force applied on the system in the frequency domain and velocity of the response, right, in the frequency domain. And then we also have what is called as apparent mass, which we can denote by say MA, and it is ratio of force applied on in the frequency domain divided by the acceleration of the response in the frequency domain, right. So these are the three inverse descriptors of the FRFs, and we see that for a single degree of freedom system, the FRFs and their inverse counterparts, they are related by reciprocal relationship. Okay. So for single degree of freedom systems, the FRF and inverse FRFs are related by reciprocal relationship, right. So therefore if I want to know dynamic stiffness, then I can determine the dynamic stiffness Z omega as reciprocal of the receptance, right. Similarly, if I have the information about the mobility, I can determine the impedance as reciprocal of the mobility. So however, this reciprocal relationship will not be valid for a multi-degree of freedom system. That is something we will study in the next lecture. Okay. Let us now study how we can present the FRFs graphically. So we are going to talk about graphical presentation of FRFs. So the first plot which is widely used to present the FRFs graphically is body plot. Okay. And this consists of a magnitude plot, okay, in which the FRF magnitude in decibels is plotted, right, versus plotted against frequency. and FRF magnitude in dB is basically given by 20 log to the base 10 magnitude of the FRF, right, that is the FRF magnitude in dB. And then we have the phase plot in which the FRF phase in degrees or radians is plotted against frequency, right, and the frequency axis can be either linear frequency axis or logarithmic frequency axis. In modal analysis often we use a linear frequency axis, but however if the frequency range of measurement is very large, then we may use a logarithmic frequency axis to show the or compress the frequency range and see the variation over that whole range, right, in a single plot. So this FRF magnitude plot may look something like this, that we have this we are plotting here the magnitude in decibels, and the plot may look something like this, and similarly we may have the phase plot which may, for a single degree of freedom system, it may look something like this, that is the phase in degrees, right. So this is basically the body plot. So advantage of this plot is that from the magnitude plot we are able to see the magnitude over the whole frequency range, that what is how the magnitude of the FRS is varying when the excitation frequency varies, and the phase plot shows the information about the phase at different frequencies. Another plot which is used is absolute magnitude plot. So in this plot the absolute value of the magnitude or the absolute magnitude is plotted against frequency, right. So this plot may look something like this. So we have the absolute magnitude, that is delta alpha absolute or alpha magnitude as a function of frequency, and this plot may appear like this. Correct. So for a single degree of freedom system it may look something like this, and we see that here because the absolute value magnitude is plotted, the peak magnitude dominates the whole plot, right, and the variation of the FRF over the frequency range or over the frequencies which are away from the resonance region, they are completely eclipsed by this peak in the plot, right, and therefore if the objective is to just see what are the peaks, what are the frequencies at which the peak response occurs, then this plot can be useful. But if the objective is to see the FRF variation over the whole frequency range, then the body magnitude plot is preferable, right. Another plot which is used is plot of real and imaginary parts, right. So plot of real and imaginary parts versus frequency. So in this case in the first plot we plot the real part of the FRF as a function of frequency, right, and this plot may look for a single degree of freedom system something like this. And the other plot consists of imaginary part of the FRF being plotted on the y axis with frequency on the x axis, and this plot for a single degree of freedom system may look like this. Okay. So real part of the FRF may look like this. Something like this. Another plot which is used to present FRF is what is called as Nyquist plot. Right, Nyquist plot. Nyquist plot is a plot of real part of the FRF versus imaginary part. Right. So, this plot may look like this. So, real part, so imaginary part we have on the y axis, imaginary part of the FRF, and the real part of the FRF we have plotted on the x axis. So, so different frequency points will be there like this, you know, and these points together, you know, when they are joined, they result into what is called as Nyquist plot. Something like this. Okay. So, in the Nyquist plot, the frequency variable, it appears only implicitly, right. Okay. So, however, we can see the variation of real and imaginary part, you know, against each other. That is the, you know, advantage of the Nyquist plot. Let us now see and study the characteristics of FRFs of a single degree of freedom system with viscous damping. So, now we are going to talk about FRF characteristics of a single degree of freedom system with viscous damping. So, we already have studied and determined the an expression for the frequency response function for such a system, and that expression is we are going to look at the receptance now, receptance of the system. So, receptance alpha omega we obtained is 1 upon k minus m omega square plus I omega c, where c is the viscous damping coefficient, right, and k and m are the stiffness and mass of the system. This expression we can also, you know, if we divide by k in the numerator and denominator, this expression can also be written as 1 by k 1 minus omega upon omega n whole square plus I 2 zeta omega upon omega n, where zeta is the viscous damping factor. We can also now determine the magnitude of the FRF, which is you know, which can be obtained as follows. We can, you know, multiply the numerator and denominator by k minus m omega square minus I omega c, right, and if you simplify, the magnitude would turn out to be 1 upon under root of k minus m omega square whole square plus omega c whole square. Similarly, for this case, the magnitude would be 1 by k upon square root of 1 minus omega upon omega n whole square, square of the bracket, plus 2 zeta omega upon omega n whole square, right. So, that is the magnitude, and of course, we can also determine the phase, right, which I can write as phase lag phi is equal to tan inverse 2 zeta omega upon omega n upon 1 minus omega upon omega n whole square, right. And for a with single degree of freedom system with viscous damping, we have got this, you know, magnitude and phase. Graphically, if I plot them, if I plot here, let us say the magnitude in dB, right, then and then frequency on the y axis, x axis, then this plot would look something like this. Right, and this is the location of the undamped natural frequency omega n. So, we see that for this system, as we have studied earlier, the peak in the FRF occurs slightly to the left of the natural frequency. Similarly, the phase plot looks like this, the phase lag here, right, and so this plot would look something like this, right. So, here the at omega n, when excitation frequency is equal to omega n, the phase is around 90 degree, is 90 degree in fact, and starts from 0 degree, and when the excitation frequency is very large as compared to the natural frequency, the phase tends to become equal to 180 degree. So, this is the basically magnitude and phase of single layer of Adamson viscous damping. Let us now try to study the behavior of the magnitude plot, right, in the low and high frequency range. Okay. So, based on this behavior, we are going to now define two asymptotes of the FRF, which are called as stiffness line and mass line. So, stiffness line and mass line, correct. So, we are basically going to study in the low frequency range how the FRF magnitude can be approximated. So, if you look at excitation frequencies which are very small as compared to the natural frequency of the system, right, that is when omega upon omega n ratio is very small. Okay. So, let us see how we can approximate the FRF magnitude. So, the FRF magnitude, we let me write that expression again here, 1 upon 1 by k in the numerator, and then we have 1 minus omega upon omega n square whole square plus 2 zeta omega upon omega n square, right. So, if omega upon omega n is very small, right, then what is going to happen? Delta alpha magnitude can be written as 1 by k, right. It can be approximately 1 by k, because in the denominator, when omega upon omega is very small, basically the denominator tends to become equal to 1, right. And now if you write this in the dB form, then we have 20 log 10 alpha is equal to 20 log 10 1 by k, right, and which can be therefore written as minus 20 log 10 k, right. So, what we see, this is the dB magnitude of the FRF, okay, and this dB magnitude, we see that it basically is not dependent on omega, right, and therefore it represents a line which is parallel to the frequency axis, the x axis, okay. So, it means that the magnitude of the FRF can be approximated by a line which is parallel to the frequency axis and which makes an intercept of minus 20 log 10 k on the y axis. And this line, because it is dependent only on the stiffness of the system, this line is referred as the stiffness line, right. So, if I show it graphically, then what we have got? We have this FRF here, FRF magnitude in dB, right. This plot is going to look like this, the FRF magnitude plot, right. And now if I show the line we got, then this line is a horizontal line which is parallel to the frequency axis, right, and it makes an intersection on the y axis at minus 20 log 10 k, and this line is called as stiffness line. So, this line very well approximates the behavior. So, if I look at in this region, right. This we can roughly mark as the low frequency region. So, in this region this stiffness line is able to approximate the magnitude of the FRF reasonably well, right. So, this is called basically the stiffness line, and it basically forms an asymptote of the stiffness line. It basically forms an asymptote of the FRF magnitude plot, right, in the low frequency range. Okay. Let us now study what happens in the high frequency range. So, in the high frequency range, when omega is much larger than the natural frequency, right. So, this means that omega upon omega n is much larger than the 1, it is very large value. And if you look at the magnitude plot, magnitude of the FRF, which is 1 by k divided by under root of 1 minus omega upon omega n square whole square plus 2 zeta omega upon omega n square, right. So, if we take this limit when omega upon omega n becomes very large, then this magnitude of the FRF can be approximated as 1 by k in the numerator, and in the denominator the term omega upon omega n square, that is going to dominate the rest of the terms, right, and therefore we can approximate that as omega upon omega n square. The denominator we can approximate as omega upon omega n square. Therefore, this can be further written as 1 by k into omega n square upon omega square, 1 upon 1 omega n square is nothing but k by m, right, and therefore what we get is that the magnitude can be approximated by the expression 1 upon m omega square, right. So, that is what we are getting as the equation that can approximate the FRF magnitude in the high frequency range. If we take now again 20 log 10 on both sides, so that we convert the FRF magnitude into decibels, then we get 20 minus 20 log 10 m, right, minus 20 log 10 omega square, which can further be written as minus 20 log 10 m minus 40 log 10 omega, and this is nothing but the dB magnitude of the FRF. So, what is the conclusion here? The conclusion is that this equation, so what is the conclusion here? From this equation we see that this equation is essentially equation of a straight line if the frequency axis is logarithmic. Okay. So, on the right hand side we have log 10 omega term appearing. So, if we treat that as the variable, right, which means that if we plot the dB magnitude on a logarithmic frequency axis, then it is basically in the high frequency range basically the FRF magnitude can be approximated by a straight line, right, and that straight line will have a slope of minus 40 dB per decade, right, and it will have an it will make an intercept of minus 20 log 10 m on the ordinate, right, at omega is equal to 1 radian per second. So, let us try to represent this on the graph. So, if we plot here the alpha in decibels and here we plot the frequency, and if this is the magnitude plot, right, and also we are plotting this on a log scale, that is log 10 omega, that is what we are plotting on logarithmic frequency axis. Then what we see that in the high frequency range this magnitude plot can be approximated by a straight line like this, okay, and the slope of this line is minus 40 decibels per decade, okay, and it makes an intercept of it makes an intercept. So, if I show here the ordinate at omega is equal to 1 radian per second, then this line makes an intercept of minus 20 log 10 m on this ordinate. Okay. And this line is basically dependent only on the mass of the system, and that is why this line is called as mass line. It is called as mass line. So, the mass line approximates the FRF magnitude, right, in dB, right, in the high frequency range. For a single degree of freedom system with viscous damping. Okay. Also, this slope of this line is minus 40 dB per decade. Slope of the line is, the slope is minus 40 dB per decade. So, why that is so? We can understand this in this manner. If I take, say, omega is, let us say 10, right, and if I look at the magnitude of minus 40 log 10 omega, this term, then this magnitude will be minus 40, right, dB. And if I increase the omega by a factor of 10, that is, I make it 100, then this would be minus 40 into 2, that is minus 80 dB. So, this means that when we increase the omega by 1 decade, that is a factor of 10, then the magnitude of the FRF drops by by 40 dB, right. So, change is minus 40 dB or drop by 40 dB, okay, and hence we say that the slope of this line is minus 40 dB per decade. So, therefore, now this stiffness and mass lines can be used to identify the mass and stiffness of a single degree of freedom system with viscous damping from its FRF plot. Okay. So, we can identify identification of mass and stiffness from FRF plot. So, if the FRF plot of a single degree of freedom system with viscous damping is available, then we can determine the mass and stiffness of the system from this plot using the concept of stiffness and mass line. How can we do that? Let us quickly make the plot here. So, this is the FRF plot, and then we are plotting it on the logarithmic frequency axis, log 10 omega, and here we are plotting the FRF magnitude in decibels. So, now to find stiffness, what we can do, we can draw the low frequency asymptote of the FRF, right, which is nothing but a straight line at in the low frequency range, and that should be asymptote to the FRF, that is almost tangent to the FRF, and then we can read where does it intersect on the y axis, that is minus, that value would be minus 20 log 10 k, and therefore we can determine the value of k from the dB magnitude, right. So, so let us say if that value is if I call that as say alpha naught, right, then I can write this as alpha naught, that is alpha naught decibels is equal to minus 20 log 10 k, right, and therefore the k would be simply equal to alpha naught upon 20, right, 10 to the power this. So, that basically becomes the value of k. Okay. Similarly, if I want to know the mass of the system, then we can determine it from here. So, we draw a asymptote, we draw asymptote to the FRF, that is a line which is at a slope of, which is tangent to the FRF curve, and it is at a slope of minus 40 dB per decade, right. So, so therefore, if I show here the frequencies which are going to be there on the y axis, they will be 1, then 10, then 100. So, this is basically going to be the different decades of the frequencies, right, 0.1, 1, 10, 100, 1000. So, now we can plot here asymptote which has a slope of minus 40 dB per decade, and let us say that asymptote is this, okay. And then we should see where does this intersect, where does this asymptote intersect on the ordinate at omega is equal to 1, right. So, if I extend it and right, so let us say this value is alpha dash, right. So, then I can say that alpha dash dB is equal to minus 20 log 10 m, right, and therefore, m would be simply equal to 10 to the power minus alpha dash by 20, that will be m, right. So, of course, we should remember that this line has been drawn with a slope of minus 40 dB per decade, right. So, that is how we can identify the mass and stiffness of the system from the FRF plot of the system. Can we identify viscous damping coefficient from these mass and stiffness lines? Estimation of viscous damping coefficient, right. So, if you look at the stiffness line, so if I represent stiffness line magnitude by alpha SL, right, SL representing the stiffness line, then at omega is equal to omega n, right. So, at omega is equal to omega n, this value is 1 by k, because anyway it does not matter at what frequency you write this magnitude, because stiffness line is not dependent on omega. The magnitude of the mass line, if I represent it by alpha ml, which is equal to 1 upon m omega square, then at omega to omega n, that magnitude would be m omega n square, and this would be again equal to 1 by k. And if I look at the magnitude of the FRF alpha itself, then that would be 1 by k divided by square root of 1 minus omega upon omega n square. So, that will be 1 plus 2 zeta omega upon omega n will be 1 square, right. So, this becomes 1 upon 2 zeta k, right. If I take the ratio of alpha and magnitude of the stiffness line, that is alpha, right, then this will be equal to 1 upon 2 zeta k upon 1 by k. So, that is 1 by 2 zeta, right. And if I take 20 log 10, then 20 log 10 alpha minus 20 log 10 alpha SL, this is equal to 20 log 10 1 upon 2 zeta, right. And the left hand side basically represents the difference in the dB magnitudes of the FRF and the stiffness line. So, if I represent, let us say this by delta alpha, then I get the relationship that 20 log 10 1 upon 2 zeta, is not it. And if I further simplify this, then I can write this as 1 upon 2 zeta is equal to that should be equal to 10 to the power delta alpha upon 20, right. And if I take reciprocal, then that becomes 10 to the power minus delta alpha upon 20. Therefore, zeta is equal to 1 upon 2 10 to the power minus delta alpha upon 20. and because we know that C upon Cc is equal to zeta, I basically get from here C as twice under root km, right, into 1 upon 2 10 to the power minus delta alpha upon 20, which basically reduces to under root km 10 to the power minus delta alpha upon 20. So, this is the expression we get for the viscous damping coefficient. Let us see that how do you determine now the delta alpha, right, from the magnitude plot. So, let us make a plot of this first. Okay. So, here we are plotting the magnitude in dB versus log frequency axis. Let us first of all make the let us say this is the stiffness line we have, and we have, let us say, the mass line, right, okay, and we know that they intersect at omega to omega n, right. So, therefore, what we do, we determine first of all the magnitude of the FRF at this frequency, and let me overlay on this the FRF like this. It is going to be like this. So, now if I extend this line like this, then this is nothing but the delta alpha, it is in dB, right. So, wherever this ordinate intersects the FRF curve, that magnitude has to be taken, and magnitude of the stiffness line. So, that is delta alpha. So, this we can read from the magnitude plot, and then we can determine the viscous damping coefficient. Let us now look at the magnitude plot again. This is in decibels, right. So, this plot is like this. So, we see that in the low frequency region, it is the stiffness which largely determines the response of the system, and hence this is often referred as stiffness control region. While in the high frequency region, we have seen that the mass line can be used to approximate the behavior or the FRF of the single degree of freedom system, and hence this region is often referred as mass control region. But if you look at the frequency range, which is around the resonance frequency, right. So, here it is the damping coefficient which largely determines the response of the system, and hence this region is often referred as damping control region. So, here we have now analyzed the the magnitude of the FRF in the low and high frequency region. A similar analysis we can do for mobility and inertance, right. So, whatever confusions we have drawn for or whatever analysis we have done for the receptance, we can extend it to mobility and inertance. So, if you do this analysis for mobility, then the FRF plot of mobility, right, y in dB, this plot would look something like this, right, and the stiffness line will have a slope of plus 20 dB per decade. So, this is the stiffness line, and it will have a slope of plus 20 dB per decade. And if you look at the mass line, then the mass line will have a slope of minus 20 dB per decade. So, this is the mass line, and it will have a slope of minus 20 dB per decade, right. And if you look at if you analyze the inertance. Then the magnitude plot would be something like this. Okay. So, this is the inertance. Let me represent it by say A is the magnitude of the inertance in dB versus logarithmic frequency. Okay. So, this is also mobility plot is also on the logarithmic frequency axis. So, in this case, so you will have the stiffness line which will have a slope of plus 40 dB per decade, and then the mass line would be a horizontal line like this, and it will have a slope of 0 dB per decade, right. So, therefore, we see that these concepts also can be defined for mobility and inertance FRF. Let us now look at the Nyquist plot, okay, of the mobility. And let us see what property it has. So, if you look at the Nyquist the mobility of the system, that will be y omega will be equal to I omega times alpha of omega, right, and I omega we had obtained as 1 upon k minus m omega square plus I omega c, right. Let us try to determine the real and imaginary part, because for Nyquist plot we need to plot real part versus imaginary part, right. So, if I multiply it by k minus m omega square minus I omega c and divide by the same quantity and then do the simplification, then I can determine the real part of y omega as that would be omega square c k minus m omega square plus I have omega c square, right, and then I will also have the imaginary part as k minus m omega square omega upon k minus m omega square plus omega c square. And now we see that this real part and imaginary part, they satisfy this equation. So, if I take real part of y, then real part of y minus 1 upon 2 c square plus imaginary part of y square is equal to 1 upon 2 c square. So, we see that the real part and imaginary part of the mobility of the single degree of freedom system with viscous damping, it satisfies this equation, and this equation is nothing but the equation of a circle, right, with real part and imaginary part plotted on the x and y axis. Therefore, we see that the Nyquist plot of mobility traces a circular trajectory. So, let us trace the Nyquist plot. This is real part of the mobility and this is imaginary part of the mobility, and this plot would look something like this. Right. So, this is the starting frequency, right, 0 hertz, and then going up to some high frequency range. So, this is now nothing but a circular trajectory, and the center of this circular trajectory, as we can see from the equation, is 1 upon 2 c comma 0, that is the coordinates of the center, 1 upon 2c is the x coordinate, 0 is the y coordinate, and the radius of this circular trajectory is actually 1 upon 2c. So, this is a very important property of the Nyquist plot of mobility for a single degree of freedom system with viscous damping, and later on we will make use of this property in one of the methods of modal analysis. There we will see that how this property is used to determine the modal parameters. Let us also look at the real and imaginary plots of the FRF for single degree of freedom system with viscous damping, and what we see is that the real part, if we plot here on the y axis of the receptance versus omega, right, on a linear frequency axis, then this plot would look something like this. Okay. So, what we know, the real part basically intersects the frequency axis at omega 0 to omega n. Okay. So, real part becomes 0 at omega to omega n, and if we look at the imaginary part, then that looks something like this. So, that reaches to the peak value at omega to omega n, like this. So, this frequency where it peaks is omega n. So, this is the behavior of the real and imaginary parts of the FRF of single degree of freedom system with viscous damping. So, in this way today we have covered the FRF characteristics of single degree of freedom system with viscous damping. I think now we can stop here and we will continue in the next class. Thank you.